Welcome muli sa lahat. Welcome to our second topic of food physics. Obvious naman po dun sa 4 picks 1 word in the title of this video kung ano yung mga words doon sa naunang 2 slides. So today, we'll be discussing mass and density. So last time, we've looked at the basis for all of our measurement of physical phenomena, which are the base SI units, and how they were developed, and even the recent developments worldwide regarding changes in the long-held definitions of some of these base SI units, which will somehow affect how we measure our physical properties of food. So let's start with probably the most common, mass and density. Right, so ever since we were young, the moment you were born, you have been put on a sort of weighing scale, and you probably encountered density from, let's say, elementary school, when you had those experiments where one liquid was put on top of the other, and um, the liquids would stratify into layers, or perhaps when you um, tried playing in the water and saw that some items floated while others sank. No? So those are all related with mass and density. Of course, unang tanong, ano nga bang significance ito sa pagkain? Well, malaking malaki. Kasi bibili ka ng kahit ano, it's usually sold more often than not by weight, or if not naman by volume. And what relates weight and volume? Aba, density. Okay, so let's start. Okay, moving on, tapos na tayo sa mass. Let's now go on to volume and density. So, balikan natin yung pako at bulak. Okay. So, alam naman natin that isang kilong pako at isang kilong bulak ay pareho ng mass. Pero alam natin na definitely mas malaki yung volume ng bulak versus the pako, and therefore we could assume that pako has a much higher density. Okay. Although foods have a relatively small range of densities, unless you're gonna take the relative density of something like puffed chicharon or corn kernels. So in reality, maraming substances have a very wide range of density. We have somewhere from a hydrogen gas, which is um, 1, 2, 3, 4, 9 raised to the minus 5 grams per cm cube ang level ng density niya. While dwarf star, which is very dense, no? Ang alam natin usually Mercury is dense, pero walang sinabi yan sa density ng isang dwarf star. Okay? So, volume again is defined as the space occupied by matter. So, in cubic meters, so it's a derived unit. Density is also a derived unit and is the ratio of the mass to the volume. So definitely any measurement of density would involve a combination of, mass measurement and volume measurement. Okay. And specific volume is simply the inverse of your density. So volume per unit mass naman. Alright, so fast facts about density. Number 1 is that it is an intrinsic property of your material, meaning regardless of how much material you have, the density would remain the same. However, density is temperature dependent, and the effect is more pronounced on gases than in liquids and in solids. So, especially in gases, you would want to consider the temperature of the gas when you look at its density. In liquids, may konti naman din, pero usually, for example, if the density of water, we have a table for the density of water at various temperatures that we could use to interpolate. So we don't always assume that it's a 1 gram per ml, because in reality, it is not. Okay, although the difference is around mga 1% or less. But in some cases, it may be critical. It's also dependent on the pressure, again, especially for gases. No? From our chem, alam natin yung PV and RT equation natin. So, magagamit din natin yon dito. So typically, we would expect the density to somewhat be on a linear scale, no, na kapag tumataas yung temperature, bumababa yung density mo or tumataas yung volume. Water is somewhat abnormal because instead of having a straight line curve, it has a different behavior from 0 to 4 degrees, wherein nagpipeak yung density niya at 4 degrees Celsius, no? And then goes either direction from there until it freezes. So in this case, we have here the thermal expansion coefficient, which is a function of is given by the change in volume over the change in temperature. So parang slope of the line lang siya. So we oftentimes see pressure as somewhat similar to a compressive force, and therefore, when there is higher pressure, there is compression happening, or nag-i-increase, nagiging mas dense yung matter. No, this is true for gases, wherein an increase in pressure will lead to an increase with a proportional decrease in a decrease in volume and an increase in density. Okay. For liquids and solids, they show somewhat elastic behavior, wherein it can be compressed under pressure but recovers upon the removal of pressure. Although under most instances, hindi mo napapansin visibly na nagko-compress yung solid or liquid under slight pressure lang from its normal conditions, no? For solids, however, not all recover upon the removal of pressure, no? So pwedeng partial lang yung recovery niya, or pwedeng nasira na yung kanyang solid structure, nag-crumble siya or something. If the K value is low, yung coefficient niya, then you could, for all practical purposes, consider the substance as incompressible, such as water with K value, yung degree niya is to the -10, okay? So here you can see that the change in volume of a substance is equal to the inverse of your K value multiplied by the change in pressure. And similarly, if you'd turn that around, in relationship niya, so the change in density, therefore, is related to the absolute value of your delta V over V, which is equal to the absolute value of your K and the change in pressure. And if you were to look at water and these proportionality equations, given the K value of water, if you were to subject water to 10 bars of pressure, you would increase its density by 0.05%, and a tenfold increase, of course, 100 bars of pressure would increase it to the density by 0.5%. 1,000 bars increase of 5% increase in density, and then a 50% increase in density with 10,000 bars of pressure. So alam ko medyo mahirap isipin yung ano ba yung feeling ng pressure na ito, but essentially, of course, that's enough pressure to crush lighter solid objects, no? Definitely. So it's possible to compress water, but you'd need a lot of pressure to do so. So to put this into perspective, alright, so makamasinda kayo sa calculus na ito. Of course, this is just the derivation of the equation relating the change in energy or the energy requirements and the relation to the pressure and the change in volume. So kung gusto nyo, tingnan nyo yung calculus niyan, but we'll focus on the problem solving. So you want the energy required for the compression of water by 300 megapascals or 3,000 bar. Okay. assuming 1 kilogram of water and given the K value for water over here. So if we put that into the equation, we would get a value of 22.5 kilojoules to compress 1 kilogram of water using 3,000 bar of pressure. So gaano ba kalaki yung 22.5 kilojoules na yan? So to put things in perspective, that is the calorific energy of 1/17 of a banana, okay, or the energy consumed by an electric fan running for 9 minutes, okay. So konti lang naman pala. Pero take note that compression typically happens instantaneously, no? So if you say that it happens in 1 second, then that's the energy of 9 times 60, 540 electric fans running simultaneously for 1 second, no? Medyo malaki nga in terms of the instantaneous energy output. And then this is enough energy to increase the temperature of your water by 5.4 Kelvin. So remember, if you can remember your law of conservation of energy, so lahat ng energy na pinang-compress doon sa water mo, hindi naman yun nalo-lost pero napupunta yun sa water. So in various forms. And one form is an increase in enthalpy or internal energy reflected by an increase in temperature by 5.4 Kelvin or degrees Celsius na delta T. So you might have already been familiar with specific gravity, but it is defined again as the ratio of the density of a certain material to a reference material, which is typically water at either 4 degrees Celsius or 20 degrees Celsius. And it is given by simply the ratio of the densities, wherein the reference material is the denominator and the material being compared is the numerator. Okay. Okay, punta naman tayo sa density measurement. No? Any form of density measurement usually involves measurement of the mass and the measurement of the volume and using and equating the two, dividing mass by the volume. No? So in the lab, we have these pycnometer bottles. Typically, these are for liquid. So fixed volume bottle sila, and then you just put it on a calibrated weighing scale and you compute the density based on the obtained weight and the fixed volume. Okay, so we look at some of these, no? Some of these we can rudimentarily do at home and some are more advanced. So again, for the pycnometer, you simply fill to the specific volume yung bottle mo and then put it on a weighing scale. And then you can measure, of course, the density based on the difference in masses of the empty bottle and the filled bottle divided by the fixed volume that you have. However, this is temperature dependent since the pycnometer is calibrated at a specific temperature, no? So you might have to use it under an air-conditioned room or perhaps use calibration factors or adjustment factors for your temperature kung saan ka man nag-work na lab. So it can also be used to measure density or specific gravity of fluids by simply comparing the ratios of the masses of the fluid and let's say your water as reference, no? So para direct comparison na siya. So just some terms for pycnometric measurement. We use the term true mass if you accounted for atmospheric buoyancy in your calculations. Otherwise, we report it as apparent mass. So here are just different examples of pycnometer bottles. As you can see, it's possible to use a regular good old volumetric flask for this purpose. Of course, you need to have an idea about its temperature calibration, otherwise there would be some errors. So next we have hydrostatic balances or buoyancy weighing. We submerge the body in a fluid, and because of being submerged in fluid, the apparent weight of that body will be lower kasi may buoyant force pushing it upward. Okay? And the amount of buoyant force is proportional to the volume of the body, and you can measure the buoyant force by using um, a balance to determine the volume, and then from there you can calculate the mass of the body and calculate for the density. Okay, continuing on. It's been almost 5 hours since I recorded the last slide, so the toddler woke up and had to take care of him for a few hours, and habang nagpapakulo ako ng nilaga. So sige, let's continue this one. All right, so um, yung hydrostatic balances, the simple way of looking at the principle of operation is, for example, you have a beaker, you fill it partially with water and then place it in a top loading balance. So you zero out the reading by pressing the tare button, and then you submerge whatever solid body that is ideally not porous, no? Um, Taking care not to touch the side or the bottom of the beaker. And then um, the weight reading on your um, balance corresponds to the weight of the displaced water, and thus would tell you the volume of the that object, so that you can calculate its density when combined with the fact that you weighed the object prior, no, in air. So in this setup, you can use it for both solids and liquids via the use of a smaller beaker, which can thus contain um, liquid samples of unknown density that you want to measure. Of course, it's given that we have measured the density of the liquid inside the beaker or the bottle. Okay, so of course your unknown would, and since you can practically weigh your sample, effectively this is used to determine the volume of your body, and combining with the weight compute for the density of the material. Okay, so first we must find out the volume of the body. So in this setup, that could be done by obtaining the difference ng mass ng the body when weighed in air on top of the balance lang, and when yung weight na nag-register once you submerge the body in the fluid, which is usually water since it's abundant. Then you divide that by the density of the fluid, and you would get the proximate volume of that body. Okay, and after that you can now also compute for the density of the body by using the mass of the body in air divided by the difference between the mass of the body in air and when submerged, and multiplying it by the density of the fluid, which should be a known value by now. So here's the setup. You can just hopefully visualize it. I have attached some video links for similar principles na gumagamit ng buoyancy measurement. So you can watch them as well for more illustration. Okay, ayan, nagpapalambot na ng gulay. Malapit nang maluto ang nilaga. Anyway, right, okay. Hydrostatic balances can also be used to measure the relative density between the fluid you're using and the density of the unknown sample, no? So to do that, you simply need to compute mass in air divided by the difference between the mass in air and mass when submerged in the fluid. So on the other hand, the reverse is also possible. For example, you have a body of known volume, like a cube or metal sphere, and you want to use it to measure the density of the unknown liquid. So, pwede nyo rin gawin yon using this equation. The difference of the mass of the known body and the mass when it's submerged in the fluid divided by the volume of the known body. Are some examples of the application? Baka napaisip kayo, bakit ang dami namang methods to determine density? So of course, definitely there are some limitations to certain in certain cases. Like for example, this method cannot be used for porous objects or hygroscopic objects that absorb moisture once immersed, diba? But at the same time, it's an easy method for certain cases, like for example, to indirectly measure the amount of starch in corn kernels. They simply measure the density, okay? Since the specific gravity range of the corn kernels relate to an optimal starch content kung kailan siya pwedeng gamitin na. So, also in potatoes, ganun din. The potato density is a function of the starch content since mostly mataas ang moisture ng patatas. And what they simply do is weigh the potatoes in air and then submerged in water, and then they determine the starch content through correlation. So maraming uses ito, no? Like syempre pag nagbebenta ka, you want potatoes to be of a certain quality, for example, and a certain starch content. So you can use this method as a rapid method of determining starch without having to rely on chemical analysis methods, no? So physical properties of food are pretty much very useful in food analysis, no? So sky's the limit lang. As long as we understand how the commodity works, then we could take advantage of changes in its physical properties to measure certain parameters about that object or food substance. On the other hand, we also have the Moore-Westphal balance for liquid samples. So we have a sort of balance here. As you can see, ayan yung arm niya. Then this one would tilt up and down from the center kung hindi na siya balanced, so to speak. And these are the weights that are added, yung parang mga clips dyan. And this is yung buoyant body mo, buoyancy body. So you just suspend it in the liquid, and as you suspend it in the liquid, gagaan siya, okay? So most likely this thing would tilt upwards and this needle would point downwards, and they'll just add clips. And then yung type ng clip and the location would correspond to a certain weight correction factor hanggang mag-zero siya. Okay, and then they use the equivalent ng added weight para i-compute yung giging density ng product mo, nung unknown sample. So definitely you have to calibrate this thing to be able to use it, but once it's calibrated, simple calculation na lang based on added weights, and then you could churn out the density of that fluid through correlation. So here's how it works simply, no? Force is equal to mass times acceleration, density times volume equals mass, and g is acceleration due to gravity. Alright, so we have here the forces. A buoyant force of your fluid is equal to the density of the fluid multiplied by the fixed volume of the fluid and the acceleration due to gravity. So all in all, you could have this ratio, okay, relating the relative density as the density of the fluid versus the density of the test reference material, which is water. But since they have the same volume, then the ratio of their masses would automatically equate to the ratio of your what do you call this, the ratio of your densities, no? So, yung amount of weights na in-add back mo to make it balanced again, divided by yung mass ng reference material mo, which is usually water, would then give you the relative density of that material, unknown material. So we also have hydrometers or areometers. These are buoy-shaped hollow glass bodies designed to float at a certain depth when submerged in the liquid sample. So I'm not sure if you've seen some of these, since these are used even outside the food applications, no? So if you look at the glass instrument, meron siyang weighted bottom, may pampabigat sa ilalim, and then usually a hollow body, tapos sa taas may mga gradations yan, no? So yung gradations na yun, depende kung gaano siya kalubog dun sa liquid mo. So yung fluid level, mag-intersect siya sa isang gradation which should indicate the density of that fluid in question. Okay. So this is obviously a very fast and very convenient way of measuring liquid samples, although you would need enough of the sample to submerge the buoy properly. And then, syempre may trade-off yung convenience niyan. It's limited to very, very specific applications. No? Kasi it works on the buoyancy principle and under the assumption, of course, that the product is water plus usually just one substance. So para siyang mixture of two substances. Kaya usually ginagamit lang siya sa sugar solutions like syrups, alcohols, acids, brine or salt, and water solutions, and even in milk where it's called a lactometer, or even in urine. No? So I don't think a food example anymore. But anyway, yun, ito, maraming iba't iba silang klase, and I think we do have some of these in the FSN lab. Ito naman, similar to the reverse hydrostatic balance technique, we have the submersion technique, which is used for high viscosity liquids. In this case, the thing na gusto mo malaman yung density is the liquid in the beaker, and yung i-immerse mo naman doon na object is yung merong known volume. Alright, so how this works is, again, you put the high viscosity liquid in the beaker, and you weigh the weight of that beaker, okay, and then you submerge a body with known volume into that beaker, and that causes buoyant forces to push upward on the submerged body, okay, and that causes a deflection in the, or a change rather in the measured weight. So that buoyant force na nasusukat ng iyong timbangan is equal to the weight of the displaced liquid, and since you know the volume of that displaced liquid, you can compute for the density of that liquid. So this is how the setup would look like. No? Typically, the test body is a hollow metal sphere with calibrated volume. As you can see, in this case, there is a depth mark to make sure that it is fully submerged. Yung pang-submerge mo sa kanya ay merong uka doon na immersed to this point. Okay, and as you can see here, so the forces acting upon it are gravitational forces and the buoyant forces, and that would cause a change in the mass na babasa ng timbangan mo. So in here we also have the particle floating technique. In this case, we have the two liquids of known densities. Tapos we should have an idea na yung solid na hindi nag-absorb ng mga liquids na yon ay merong density na nasa pagitan ng dalawang liquid. So what we do, of course, is we first put the lighter liquid in the beaker, and then we also place the sample itself. Dahil mas mabigat siya dun sa lighter liquid, it will sink to the bottom. Then you will slowly mix in your denser liquid until the material na yung solid mo starts to float, and then at that point you stop, and then you calculate the density of the mixture, which is, alam mo naman, since you know the volumes of both and densities of both of the two fluids, no? So here's an illustration. If you do it, let's say in a graduated cylinder or in a relatively tall beaker, so makita mo naman unti-unting mag-float pataas yung object mo hanggang sa well, probably it would stay somewhere around the middle kung nag-stop ka agad, no? Which means the particle at that point has more or less the same density as the combination of the two fluids. Now, what would you do if the particle would react with the liquid? No? So you can use a different liquid, or you can coat that particle with something thin enough na hindi maapektuhan yung density, but at the same time would prevent the reaction with the liquids in question. Dito naman sa density gradient column used for agricultural seeds or grains, so you have a column filled with fluid that has a density gradient, meaning mas malapot sa ilalim, mas mas light sa itaas, and then you slowly submerge yung grain or of whatever object mo until it stops, no? And or remains suspended in a certain place. And of course, you could mark with gradations na corresponding to the density yung places doon sa column mo. So the columns layers are mixtures containing different proportions of two miscible transparent liquids. So here are examples of the different combinations ng liquids na pwede mong gamitin and the specific gravity range based on, for example, in this case, 100% isopropanol is 0.79, 100% water is a specific gravity of 1. So they use colored beads calibrated with a certain density para makita yung positions doon sa column mo. Like if a bead floats at a certain height and you know that color corresponds to a certain density, then yun yung magiging parang markers mo. So typically what they do here is, example, the bottom layer is 100% high density liquid. So kung dito yung isopropanol water mo, the bottom layer is pure water. Then they would add a layer of 90% water, 10% isopropanol, then 80% water, 20% isopropanol, hanggang sa mag-zero water, pure isopropanol na yung taas. Okay, so that's an example of using it. Okay, so we also have what we call resonant frequency techniques. This is used for liquids. The principle is that you calculate the density of a fluid inside a U-shaped oscillating tube through monitoring the resonance frequency of the tube. So the resonance frequency is based on the mass of the U-shaped tube, or rather the fluid inside it. So ang advantage nito is it can be used for inline monitoring, meaning, for example, if you have liquid flowing in a tube, such as maybe during the pasteurization of fruit juices, in real time, imbis na kukuha ka pa ng sample dun sa gripo dun sa tubo or whatever, or magsasando ka sa tangke, magbabypass ka lang ng dumadaan na fluid dun sa tube mo. And then as it oscillates, it correlates the resonance oscillating frequency with the density of the fluid inside it. So high-tech siya, but although of course you still need some sort of calibration for it, and that's why usually it's used in mostly quality control purposes, wherein ilan lang yung products na ginagawa mo on that production line, and you have very specific density ranges to note. Next is overrun. Hindi po ito mawawala. Ako po ay galing sa ice cream industry. And I'm not sure sa FN102 if you still discuss this, no? This is used for aerated fluids such as cream or ice cream, no? So may hangin sa loob, yung iyong liquid, may gas component. So the overrun is a dimensionless ratio expressing amount of aeration under the assumption more or less na very negligible yung timbang ng hangin sa loob ng product mo, like close to zero. So aeration causes an increase in volume and therefore a decrease in density. So again, your assumption is a negligible mass of air, and we simply measure this through weighing fixed volumes of the foam and liquid separately. So sa ice cream, for example, kukunin namin yung mixed density, which is yung density ng ice cream ingredients before siyang malagyan ng hangin. And then yung lumalabas dun sa freezer, kind of like yung sa soft serve sa mga McDo, 7-Eleven, ganon. You measure a fixed volume of that as well, and you compare the ratios of the densities of the liquid and the foam, okay? So and you subtract 1 from that value, no? So typically this is expressed in percent. So 100% overrun means that nag-double yung volume ng liquid mo, and 0% overrun means walang hangin. Typically, yung mga ice creams ninyo have more or less 100% overrun. It could go as high as 130 for yung medyo low end na ice cream, and as low as 70 for the high end denser ice creams. Okay, gising na ang aming toddler. It's almost 11 a.m. and luto na rin ang aking nilaga. So I guess I'll stop here. The next part was solid density, which is medyo tricky, lalo na for porous solids or those that absorb water. However, one thing we should consider for porous solids is whether or not pore volume is included or excluded from the calculation. So as we can see, powders, which are essentially solids in air, no, appear much lighter than they are, pero pag vinacuum pack mo, pwede tinanggal yung hangin, mas magiging dense sila. So of course, both densities are useful kasi syempre, you would want to include the porosity in the equation when, or practical purposes, ipapack mo siya in a container or something na hindi naman airtight or hindi naman vacuum packed, etc. Diba? So, mas kailangan mo ng mas malaking container kasi may hangin na kasama yon. Alright, it's 4 a.m. the next day, hence the change in costume. So, for powders, there's a term that we call bulk density. So again, this applies to particulate matter suspended in air such as flour, sugar, salt, spices, and etc. Ito ay makukuha by measuring the bulk volume of the material with known mass, or rather measuring the mass of a fixed volume of a certain material. So what's important here is that you should take bulk volume as is and not compressing the contents. So to do this, we usually use machines that tap the container with modulated amplitude and frequency so that a sort of natural settling due to gravitation will occur. Okay, di ba parang minsan kapag gusto mong mag-level yung powder sa isang beaker or what, you tap it on the side, or maybe when you're, I don't know if you do it when you're baking, but you don't apply external force with your hand or any other tool to artificially compress it versus how it would normally settle. So here is an example of an equipment for testing bulk density. As you can see in this illustration, the particulate matter is not of a uniform size. We will discuss that in a succeeding chapter though. So here's the actual appearance of that machine. And what happens is this rotating cam rotates and then sort of taps this container up and down, thus having a settling now of the solids inside the cylinder. And after that, they could weigh they could obtain the volume based on the fixed weight or obtain the weight based on a fixed volume. Okay, so you can watch the video on this link for an example of a bulk density measurement machine for inline analysis, meaning to say as the product is being produced at any given time or interval, they can take samples from the line and measure the bulk density of that powder or granular form food product. Unfortunately, I cannot embed the video here for copyright infringement issues of any sort that may happen. No? So you can just click this link and watch it and read the description on the website. So powders are sometimes treated as sort of similar to fluids that flow, and the term for this is powder flowability. And the simple way of determining this is through the Hausner ratio, meaning to say the quotient of the tapped bulk density versus the untapped bulk density. So in short, kapag mas less yung difference ng tapped versus untapped bulk density, ay mas free flowing siya. If it's something that settles with tapping, meaning to say they push the air out, no, then it will be more difficult for it to flow. Powder flow in itself is a ano to, part siya ng rheology, no? Study of well, textures and flow measurements, including viscosity. And certain companies like Brookfield, who creates viscometers, specialize also in powder flow, no? Kasi sa industry, one big problem they have is those who don't have enough food physics knowledge on powder flow, nagde-design yung engineers na mga systems for material handling, like yung dinadaanan ng mga bulk powders from storage to let's say the production area na parang mga pipes or ducts, and then the powders get stuck for many reasons. Of course, na mali yung angle, kulang sa force ng pag-push ng powders, or mali yung shape and size ng mga pipes or ducts nila, or maybe yung moisture, nag-absorb ng moisture, nagkikake yung powder. But nonetheless, crucial ito no, na malaman natin how the powder flows, because if the powder gets stuck and hindi mo siya kayang manumanuhin kasi tubo yun na hindi kasya yung kamay ng tao, madedelay yung production mo sa plant or whatever, no? Just because of that one ingredient that you can't get out of the pipeline, and you'd have to probably manually transfer from the storage to your production. And you have to deal with it on a scale of tons. So hindi pwede yung may kargador kang nagdadala ng 10 kilos at a time or 20 kilos at a time for how many thousands of kilos of powder, no? Lastly we have porosity now, which is simply the ratio of the volume of the void space or air in between the solids versus the total bulk volume. Okay, so it's expressed in this way, and we know that the volume of the hollow space is equal to the volume of the bulk volume of the material less the total volume of the solid part of that bulk, okay, over the bulk. So we can rearrange it in this manner, and if we assume that the mass of the bulk and the mass of the solid material is the same because air's mass is negligible in the process, then we could rearrange this equation to give us porosity as 1 minus the quotient of the density of your bulk density versus the solid density if all of the air was removed, no? So this means that the porosity would therefore have a value of 0 to 1. 0 if the bulk volume is equal to the solid density, and therefore this would be 1 minus 1. And of course, it would be closer to 1 if the bulk density is very low. Okay, so but definitely a porosity of 1 is next to impossible. That would be pure air. Maybe one particle in a lot of air, no? So ano naman ang use nito? Definitely, of course, if you're wanting to mag-vacuum pack ka ng powders, the higher the porosity, the more compressed probably your powder will be afterwards, no? So that's one example of it. Of course, there will be many other uses for this one, especially if you're in the powder flow industry. But that is to say, we acknowledge that this is a science in and of itself na needed ng mga industries, no? Especially in the food industry. So looking back in this module, we first discussed the definition of mass and some history with regard to the prototype kilogram and how we define a kilogram now, which is the basis for all of our mass measurements, no? And then tinignan din natin kung paano ba sinusukat yung mass, ano yung difference ng scales and balance, ano ba yung important criteria when, let's say, looking at an analytical balance and the jargon involved in that, and the ways in which different electronic balances work, whether they use a deflection type method or yung electromagnetic forces na, okay? Then we looked also at volume measurement, which is when you combine with mass measurement, you can measure density, and that there are different density measurement methods, especially in whether or not you are using a solid, a liquid, or maybe a powder form solid na material. So there's an appropriate method for each one, and that there are a lot of methods that are very specific to certain applications, and that we weigh the yung use niya, no? If it's a limited use, usually mas mabilis siya, pero sa isa o dalawang bagay mo lang siya pwede gamitin, whereas the more general methods that obtain the weight and the volume through various means, most notably yung buoyancy, they can be used for a lot of applications. And some have different machines na specific for one thing yung ginagawa, and these are used for specific purposes such as mass production of powders or certain other liquids which integral yung density sa kanilang properties. Okay, so and we also knew that we can correlate density with a lot of things such as starch content in certain agricultural produce, and therefore density measurement can be a proxy measure for some other thing, as long as we know the properties of that product and how density relates or correlates with those things. So yung correlation pretty much useful pa rin sa atin ngayon, no? Anyway, so what's important to note here is that especially for density, as long as you can get the mass and the volume of a product through whatever valid scientific means, then you can measure some sort of density with a certain level of accuracy. And of course, mass measurement will always be dependent on how good your balance is. So don't forget your calibration. Okay, that's it, and you may have a good rest of your day. So time check, it's 4:20 in the morning. So in my case, good morning to you all.